most of these things that exist out there in nature. So we've got a long way to go.
Oh, fantastic. I don't know, I think it'd probably be useful if you mentioned a little bit about what BioBricks is in the registry.
Right. Okay. So the basic concept of BioBricks, and I refer to it more generally as standard biological parts, is that you have DNA elements that are all held in a common vector, and they can be assembled using one type of reaction, a standard assembly reaction, into these larger composite parts. So it's a little bit like you've got a set of different beads in your toolkit, and each one of those beads is a different basic part, and you have some means of stringing them together using one, repeatable procedure into a long necklace of beads that is the composite part. So BioBricks, more specifically, is a particular way of doing this sort of standard assembly. So it's a particular reaction that has been developed outside of MIT, was initiated by Tom Knight, but it's become very popular within the IGEM community in particular. It's based on restriction enzymes and ligation. And the result of it is you get an 8 base pair scar sequence between the various parts. But it's by far the most popular standard assembly mechanism. But there are other competing ways of doing it that are all at play today, and I think it remains to be seen exactly where all this is going. But in general, people don't like scar sequences in the standard assembly schemes, so people who don't like that tend to prefer PCR-based standard assembly schemes. There's one based on sewing, there's one based on, so sewing is a PCR trick. There's one based on a method called SLIC, which has gotten a lot of popularity in some labs. And there are methods that use type 2 restriction enzymes. There are lots of these. There are lots of ways to assemble 2 DNAs into 1 DNA. And it's not clear yet what is the best way and what ultimately will find common usage in the long term. But I think the thing that will win that battle in the end is the thing that scales well with price and can be readily automated, and the infrastructure exists for delivering that synthesis at low cost. Didn't make much sense, did it? I mean, the thing that will win that battle in the end is whatever standard assembly method is able to deliver some sort of facility that's providing as a service low-cost synthesis, fast, and large scale. A little better.
Okay, so now, what is IGEM?
IGEM. So IGEM is patterned after robot competitions. The difference is they're not making robotic machines, they're making cellular machines. And in part, it's an educational program directed towards undergraduates, and in part, it's real science. I mean, they're doing cutting-edge research, trying to develop the next generation of projects within the field of synthetic biology. And one of the great things about IGEM is that it's very exploratory. There's a lot of emphasis on new ideas and a low emphasis on results. So you don't necessarily have to make your system work for it to be a good showing at the Jamboree. It can be totally a failure, but if it's a new idea, I think people will like it. And that's one of the fun things about it, is there's a lot of creativity in the program, and a lot of new ideas, a lot of energy, a lot of young people excited about getting into the field. But in general, the way IGEM works is there are about 80 teams this year. They come from all over the world. I mean, there are teams in China, there are teams in Europe, teams in South America, everywhere. And they're all competing to make the best genetically engineered machine or an engineered cell that does something really cool. So things like You know, the first year they did it, the big thing was a light sensing E. coli, and you could capture images on a biofilm of E. coli on a plate. And then the year after that, what was the big winner? Oh, it was the Slovenia team that had engineered mammalian cells to, I don't even remember what they did. But it was really popular. Yeah, should we move on? Or what else should we say about IGEM?
Well, when did it start?
So IGEM let's see. So 2008, 2007, 2006 were full-on competitions. 2005 was the first year that it was a competition inviting many schools, but the award aspect of it and the judging aspect of it was kind of loose. And then the year before that, so I guess 2004, I think that was the year it was just out of MIT, and it wasn't exactly a competition so much as a workshop.
And so you have been working with IGEM just for this year and last year, or?
This will be my third year doing the IGEM program at UC Berkeley.
And what is this year's UC Berkeley IGEM project?
So the core of this year's project is around the idea of sound-induced self-lysis. So I think the tentative name for it is lysosonics. Lysophonics. Wait, lysophonics.
No,
okay.
lysosonics.
I don't know. Sound-induced self-lysis. So the idea is we're going to make bacteria that can sense sound and respond to it by lysing themselves, by popping. And the useful aspect of that device, besides it being cool that they're popping due to sound, is that so the nice thing about sound as a means of inducing activity in a cell is that it's externally administered and it's transient. So light, radiation, magnetic fields all have this property that they're only there while you're applying them. Afterwards, they're gone. Most induction systems, though, are based on small molecules, and there you add them and they stay there. You can't take them back out easily. You could wash it out, I guess, but you don't normally do that. So you can externally administer it. So you could have a sample and you have a speaker and you hold it over it and play sound at it and you're adding the signal, but then you turn the speaker off and it's gone. So it's very easy to administer this transiently and to a lot of samples all at once. So there's no liquid handling associated with it. And so that would be good for sort of many sample scenarios. So these sorts of high throughput applications in the laboratory. So high throughput purifications, high throughput chemical reactions, high throughput screening, these sorts of things. And so we're building this core device, this sound-induced self-lysis device. And then we're going to try to do some of these small applications based on it. And in particular, what we've chosen to try to do is, first of all, to show we can purify protein from the lysate after sound-induced self-lysis. So this would be a means of doing very high throughput protein purification on small scale. We're also looking at trying to do the gateway reaction within the lysate. And third, we're going to try to do a standard assembly reaction within the lysate.
So those all have to do with the changing of the way you do synthetic biology.
Right. All of these are foundational technologies either directly for synthetic biology or other related fields. I mean, high throughput purification of proteins isn't necessarily a synthetic biology application. It probably has more relevance to protein engineering. That sort of scenario. Although I view protein engineering as a special case of synthetic biology. In fact, it's especially